So the bomb calorimeter was constant volume. This is constant pressure calorimetry, which is much more low tech. So here we have an illustration of what we affectionately call a coffee cup calorimeter. And this is the type of calorimeter that we're going to use when we do our experiment 6B. So this is 2 nested styrofoam cups. We use 2 cups because it gives better insulation than just 1 cup. And you probably know from experience that if you've got hot chocolate or hot cocoa in like a plastic or a paper cup, your hands get really, really hot, right? Whereas if it's in a styrofoam cup, the styrofoam insulates the beverage from your hands, helps it to stay hot longer. So here we're using 2 styrofoam cups just to give us better insulation. This one's fancy. It has a loose-fitting cork lid. Our lids are very old pieces of cardboard. Some of them are older than you are. Seriously. We use them over and over and over again. And we stick a thermometer in there. And sometimes we put a glass stirring rod in there, or sometimes we use the thermometer to stir. Really shouldn't do that because you can break the thermometer. But it's hard to break a thermometer on a styrofoam cup. Stirring it in a beaker, very easy to break the thermometer. Okay, let's stop talking about that. So the heat of reaction, that is Q, right? It's the heat absorbed or released. So we can measure that in a coffee cup calorimeter. This is constant pressure because it's not sealed off, okay? So Q for the solution, so there's a solution in here. Most of the reactions that we look at occur in aqueous solution. There's a solution in there. We can measure the mass of the solution. We can identify the specific heat capacity of the solution, and we can measure the change in temperature of the solution. The reaction is occurring inside the solution. So Q reaction is negative Q for the solution. So if I have a chemical reaction going on in there and the temperature goes up, why did the temperature go up? Where did the energy come from? It came from the chemical reaction, right? The chemical cold pack, right? You mix it together and it gets cold. How does it do that? It's absorbing energy from the surroundings. The chemical reaction is not the cold pack. That's occurring inside the cold pack. But it's absorbing energy from the other parts of the cold pack. So we're measuring the temperature of the solution, and the heat absorbed or released by the solution is the same value as the heat absorbed or released by the chemical reaction, but the sign is opposite. So Q reaction is negative Q solution, just change the sign, and that's equal to the heat of reaction. Now, heat of reaction is generally expressed per mole of substance, and it's generally specific to the chemical reaction. If we need that, then we just divide by the number of moles. There's a problem with a whole bunch of words. Okay, so the addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. That's nice. When 50 milliliters, who cares, right? We have an exam coming up. We're going to pretend to care. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Okay, so the temperature in the calorimeter went up. Where did the energy come from for the temperature rise? Not from the surroundings. From the system, and the system is the reaction. Okay, that's a bit hard to get your mind around because you can't really see the reaction, right? The reaction is occurring in the liquid, and so it's really easy to get mixed up and think, well, the liquid is the system. The chemical reaction is happening in the water. The chemical reaction is where the energy is coming from or going to. So in practice, these calorimeters do lose a little bit of heat to the air outside, but we're going to ignore that for now. So we're using the calorimeter as the surroundings. We're measuring the temperature change there, and that tells us how much energy was released by the reaction. It's hard to get your mind around, I know. So we've got this temperature change. We're supposed to calculate delta H, the heat of reaction, for the reaction as written. Yeah, that was startling. Use 1 gram per milliliter as the density of the solution and a specific heat capacity of 4.18 joules per gram degree Celsius. Okay, so what do we have going on here? So we have Q reaction and Q solution. The reaction is occurring in the solution. The solution is the aqueous solution, and the water there is absorbing the heat and rising in temperature. We want to know Q reaction, but Q for the solution is what we can calculate. Q equals MC delta T. So Q equals MC delta T. Well, we need to know the mass of the solution. They didn't give us the mass of the solution. When we do this in lab, we're actually going to stick the calorimeter on the balance and weigh the solution. But they gave us volumes, 50 milliliters of this one, 50 milliliters of that one, and they said use this for the density. So what's the total volume in the calorimeter? What's 50 plus 50? You can do it. 100, right? 50 plus 50. I'm not trying to trick you here. So our volume is 100.0 milliliters. And then we can use the density to convert that into a mass, right? This is something that should be very simple, and yet students tend to just like completely overlook this. And this is one of the reasons why I wanted you to learn how to use density as a conversion factor. You don't need the D equals M over V and algebra and all that stuff. This density is a conversion factor between mass and volume. So I've got milliliters in the bottom because I want that to cancel out, and grams on top. So the density is 1.00 grams per milliliter. So if that's the case, then 100 milliliters is 100.0 grams. Okay? So the mass of the solution is 100 grams, 100.0 grams. The specific heat capacity is given right here. So that's 4.18 joules per gram degree Celsius. And the temperature change is going to be the 24.21 minus 23.4, the final minus initial. So 0.81 degrees Celsius. So we look at the units, and the grams cancel and the degrees Celsius cancel, and we're going to have a unit of joules. So I've got 100 times 4.18 times 0.81. 338.58. And that would have two significant figures. And that is joules. So this is the amount of heat absorbed by the solution, the amount of heat released by the reaction. The reaction was 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar HCl. The question wants us, and this is really the tricky part, the question wants delta H for this equation. So if we've got delta H up here, well, first of all, is that going to be negative or positive? It's harder than it sounds. So here, this was, what is this? Q, this was Q solution. So Q solution was a positive number. That equals negative Q reaction. The solution got warm because the reaction gave off heat. So this is an exothermic reaction. Negative Q reaction equals positive 338. Q reaction then is negative 338. There are different ways to think about this, and you need to come up with the way that makes sense to you and then stick to it. So if Q is negative, that means that delta H is also negative. So this is going to be a negative number. It was this amount for this amount of stuff. So what I need is, I need the amount of heat for 1 mole of silver nitrate, right? Can I figure out how many moles of silver nitrate were in here? Yeah, 50 milliliters times 0.100 molar. Where should we do that? Let's do that. We'll do that in a different color. So 50 milliliters, let's convert that to liters, times, and this is where I'm still seeing weird things when you do your labs, 0.100. That capital M is, is not useful in this equation that I'm writing. Because how does capital M do anything with L, right? Capital M stands for what? Moles per liter. Capital M is not an abbreviation for mole. MOL is the abbreviation for MOLE, okay? Capital M means moles per liter. So write it out that way. The capital M, moles per liter. So the liters cancel, and that's going to give me moles. So 0.1 times 0.05. 0.005. But that actually has 3 significant figures because this had 3 and that had 3, and so I need to throw some zeros on there. That's how many moles actually reacted. So I've got this amount of energy for this amount of moles. So if I want to know how much energy for 1 mole, I can take this minus 338.58 joules and divide by the actual number of moles. And get 67716. And that would be joules per mole. That's a big number. Can you see why we often use kilojoules per mole? So if we make that kilojoules, I'm going to move the decimal point over 3 places, so we'll put a decimal point right there. We get kilojoules. We should have 3 significant figures. So 67.7 kilojoules per mole, and it's negative. I lost the negative sign. So up here, minus 67.7 kilojoules per mole of that. Any questions? Yeah.
Are you just using the silver nitrate?
That's a good question. Why am I just using the silver nitrate? Well, it would be per 1 mole of this and per 1 mole of that. And so we really should make sure that we have enough HCl. Because if there wasn't enough HCl for this to completely react, then we'd have a problem. So if we look at the HCl, it's the same volume of the same concentration. So it's going to have the same number of moles. So it's also 0.005 moles of HCl. So it was just the right amount of each. So we could do it with either one.
Since it's the delta H of the reaction, why don't you add those two together?
That's a good question. Why don't I add them together? Because it's this amount for 1 mole of this, for 1 mole of this, for 1 mole of this, for 1 mole of that. I have 0.005 moles of this and 0.005 moles of that. I don't have 0.01 moles of either of them. Okay, because I've got some of this and some of this. When they come together, it's still 0.005 moles. Any other questions? Yeah.
Also, if they didn't give you the density, could you just use convert them to moles and then just add together?
If they didn't give us the density here, we'd have a problem. Because we've got a volume here, and we can calculate the moles of silver nitrate in there, and we could calculate the mass of silver nitrate, but what we need is the mass of the whole solution.
Doesn't the solution just comprise of those two reactants?
Well, it does apply to these two reactants, but the mass is more than the mass of the silver nitrate and the mass of the HCl. It's also the mass of the solvent. Now, if you've got an aqueous solution and there's no density in sight, and you've looked at all the different possibilities and you're like, man, I really need a density here. Most aqueous solutions have a density very close to 1 gram per milliliter. Any other questions?